Okay, this is a video to talk about division of complex numbers, graphing complex numbers in the complex plane, and finding the absolute value of complex numbers. To start off, we are going to solve a couple equations, 3 equations, and the first thing we're going to do is we're going to identify the best way to solve them. Number 1 just says x squared equals negative 25. So the best way to solve this problem is to just take the square root of both sides. And when I take the square root, I want to remember that it could be positive or negative. And the square root of negative 25 is going to be plus or minus 5i. Because the square root of 25 is 5, and the square root, and because it's a negative 25, it needs to be 5i. Another way to think about that is like the square root of 25 times the square root of negative 1, and then it's 5i. Number 2, we're going to solve it the same way. We're going to take the square root of both sides, and that's going to give us x plus 3 equals plus or minus the square root of negative 24. Before I subtract the 3, I'm going to reduce the root 24. First off, there's a perfect square that goes in, which is 4. And that would leave 6. And then there's also a negative 1, because it's negative 24. So we've got x plus 3 equals plus or minus 2i root 6. Then we're going to subtract 3 from both sides, and we've got negative 3 plus or minus 2i root 6. For number 3, we're going to look at it, and the way it looks, I'm wondering if I could factor. I see a 40 and I see a 6, and my first thought is 4 and 10. But the problem is that to multiply to a positive 40, we're going to have either 2 positive numbers or 2 negative numbers. And to get a negative 6, we would have to have one of each, so that's not going to work. So I think what I'm going to do to solve this, since factoring doesn't work, is I'm going to try to complete the square. I know it's a good idea to complete the square for number 3 because it's already a 1x squared, and my b value here is even, so it'll be easy to do b over 2 squared. You can do the quadratic formula if you wanted, but you're probably going to end up with more reducing that way, so I'm not going to do the quadratic formula. I'm going to start by subtracting 40 from both sides, and then my b value is negative 6. Negative 6 divided by 2 is negative 3. Squared is 9. So now I've got x squared minus 6x plus 9 equals negative 31. I'm going to rewrite the left side as the square of a binomial because it's a perfect square trinomial. Now when I take the square root of both sides, I'm going to get x minus 3 equals plus or minus the square root of negative 31. There are no perfect squares that divide into negative 31, but I can rewrite it as I root 31. I'm going to add 3 to both sides, and my final answer is 3 plus or minus I root 31. I want to point out, if you had used the quadratic formula to solve this, underneath your square root, you would have had something bigger that reduced. By completing the square, we have the least arithmetic. Number 4 is just asking us to multiply. We want to remember that we need to write the binomial twice because we're multiplying it to itself. 3 times 3 gives us 9. Then we've got negative 15i, another negative 15i, and then plus 25i squared, just enough room. Well, I squared, since I is defined as the square root of negative 1, if we square both sides, the square and the square root cancel out. And we've got 9 minus 30i, combining the 15s. And so then plus 25i squared becomes plus 25 times negative 1. So really here we have 9 minus 30i minus 25. So this is going to become negative 16 minus 30i. Alright, last night's homework covered addition and subtraction and multiplication of complex numbers as well as a little solving. As always, if you have any questions, please go see your teacher at lunch. Okay, today's lesson is on division of complex numbers, graphing complex numbers in a complex plane, and then using that to find the absolute value of a complex number. The first thing you need to do is pause the video and write down these two vocabulary words. All right, two conjugates are just binomials with opposite signs between the terms. So for example, 2x plus 1 and 2x minus 1. What's special about conjugates is if you multiply them together, you end up with another binomial. And these should look familiar because if we factored perfect squares, this is what it looks like. So for example, if you had x squared minus 9 and you were factoring it, it would be x plus 3 times x minus 3. Okay, this is what we started with, and these two binomials are conjugates. When you multiply conjugates together, what happens is that the inner and the outer terms cancel. We're going to use this fact with complex conjugates to help us divide. Complex conjugates are complex numbers with opposite signs between the terms. So like if we had a plus bi, its conjugate would be a minus bi. Now, you see how these canceled out? Take a look at number 1. We're going to divide each expression. You can't divide complex numbers by just doing 3 over 5 and then 3 over, negative 2i. You can't split a denominator that way. What you're going to need to do is multiply by the equivalent of 1. And the equivalent of 1 we're going to use is the complex conjugate. When we distribute in the numerator, we get 15 plus 6i. When we multiply the denominator together, we get 25 plus 10i minus 10.
Attention members of ILT.
Sorry about that. Minus 10i minus 4i squared. Well, let's take a look at our denominator here. What's so nice is that right here, positive 10i and negative 10i cancel. We have minus 4i squared. That's like minus 4 times negative 1, which becomes plus 4. So we get 15. Whoa, I don't know what that was all about. We get 15 plus 6i in the numerator.
John, Paul, Fox, please repeat.
We have 15 plus 6i in the numerator. Sorry about that. The PA keeps turning on. And then, let's see, 25 plus 4 is just 29. Now, the directions say to divide each expression and leave our answers in standard form. This is not standard form for a complex number. To have standard form of a complex number, we have to separate the real from the imaginary. And there's our quotient. I want you to look at what happened here. We didn't actually do any dividing. We kind of canceled out the i's in the denominator so that we could split the real from the imaginary. So for number 2, we've got negative 1 plus 4i in the denominator. So we're going to multiply by negative 1 minus 4i over negative 1 minus 4i. That's going to give us, now here, number 1, we could just distribute. Well, in number 2, we're going to need to really be careful because we have 2 sets of binomials to multiply. The numerator is going to become negative 1 minus 8i minus 1i minus 4i squared. The denominator is going to become 1 plus 4i minus 4i minus 16i squared. If we simplify the numerator, this negative 4i squared we know is negative 4 times negative 1, so this just becomes positive 4. So then negative 1 plus 4 gives us 3. Negative 8i minus 1i gives us minus 9i. Negative 16i squared, well, first off, these 4i and negative 4i cancel, which is what is supposed to happen when we multiply conjugates together. And we've got negative 16i squared, which is negative 16 times negative 1, which is positive 16. 1 plus 16 is 17. We take our answer, we separate the real from the imaginary, and our answer is 3 over 17 minus 9 over 17i. Take a moment, pause the video, and try number 3 by yourself. Okay, for number 3, our denominator is 5 plus 3i, so we're going to multiply by 5 minus 3i over 5 minus 3i. The numerator is going to give us 30. Outside will be minus 18i. Inside will be minus 10i. Last will be plus 6i squared. In the denominator, we're going to have 25 minus 15i plus 15i minus 9i squared. Well, in the numerator, this is going to become minus 6. In the denominator, this is going to become plus 9 because we're going to take care of our I squareds. And again, conjugates, insides, and outsides cancel each other out. That's the beauty of
Joe Clark.
All right. So, in the numerator, we've got 30 minus 6, which is 24. And then we've got minus 28i. And then these have canceled, and we've got 25 plus 9, which is 34. So we've got 24 over 34 minus 28 over 34. And we have some even numbers, so we better reduce. I'm just going to think really simply. I mean, they're both even, so this is going to become a 12 and 15, and this is going to become a 17. So I've got 12 over 17 minus... Well, same thing, even numbers. This is 14 and this is 17. So minus 14 over 17i. And that, my friends, is division of complex numbers, where there actually is no division going on, just a whole lot of multiplication. All right, today we're also going to look at graphing complex numbers in a complex plane and using that to find the absolute value. These may look familiar to you. We used to call these x and y. Well, now we have the real axis and we have the imaginary axis. This number is 2 minus 3i. Its real component is 2. So on the real axis, we'll go 1, 2. Its imaginary component is negative 3. So we're going to go down 3. And graphing this complex number, okay, so we first start by plotting the point 2, negative 3, because 2 is the real component, negative 3 is the imaginary component. Then to graph a complex number, it's going to be represented with an arrow. So I'm going to draw an arrow from the origin to 2, negative 3. So when we look at 4i, well, does it have a real component? No. So we're not going to go right or left at all on our complex plane. We're just going to go up 4. So we're going to go up 4, put a point, and then we're going to put an arrow to that point. All right, last off, why don't you try graphing negative 1 plus 5i. Okay, to graph negative 1 plus 5i, we should go left 1, because on the real axis it's back 1. And then on the imaginary axis it should be up 5. So we're going to make an arrow from the origin to the point negative 1, 5. Okay, now why do we do this? The reason is we need to be able to find the absolute value of a complex number. If I want to find the absolute value of 2 minus 3i, what I really need to know is how far, that's an A, how far is this from 0? And the problem is, when I find the absolute value of a regular number, I can just count on the number line, back and forth. But for a complex number, because there's a real component and an imaginary component, I need to use a complex plane. So if the absolute value tells us how far something is from 0, we're looking for how far is this complex number from the origin. So I'm really looking for the length of this green arrow. Well, let's think. If we're looking for the length of this green arrow, we can make a nice little triangle here, and it's a right triangle. This has a length of 2, and this has a length of 3, or negative 3 if you want to think about it as down 3. How could we find the length of the arrow? We could use the Pythagorean theorem, and we could say c squared equals a squared plus b squared. So the absolute value of 2 minus 3i, and some teachers will teach it like this, with a negative 3, because they'll literally take whatever number is here and put it here, but you know that really doesn't make a difference because it's still going to be 4 plus 9. And so c is going to be the square root of 13. The absolute value of 2 minus 3i is the square root of 13. Now, our second example is a little easier. How many units away from the origin is 4i? Well, we just went up 4, so obviously the absolute value of 4i is just 4. If we were to use our formula, there is no real component. The imaginary component is 4, and then the square root of 16 is 4. To find the absolute value of negative 1 plus 5i, a little longer, take a minute, pause the video, and find it yourself. To find the absolute value of negative 1 plus 5i, which is the length of this lovely green arrow, we're going to do the same thing, which is take the square root of the real component squared plus the imaginary component squared. Notice that I don't put the I here, I just put the 5. And that would be the square root of 26, which doesn't reduce, so we're done. Pause the video and real quick find the absolute value of these 3. For number 1, it's going to be the square root of 3 squared plus 4 squared, which is the square root of 25, which is just 5. For number 2, again, because there's no real component, there's just an imaginary component. If I were to graph this, I would just be going down 2. So the distance from the origin is 2. For number 3, this is the same one we did on the last page. Well, that's silly. It's the square root of 26. I remember from the last one, it's negative 1 squared. No! Plus 5 squared, which was the... where'd my cursor go? Which is the square root of 26. Your homework tonight is practice 5.4a, and numbers 7 to 36, and making practice fun 42. I'm going to turn the page, so if you want to, you can pause the video and check your answers as you go. Here are the answers for practice A. And here are the answers for making practice fun 42.